Our next problem, that is the fifth problem, is a very important problem. It appears to be a bit lengthy, but it is, in reality, it is a very conceptual problem. The tangent at a point P1, which is other than origin, on the curve y equals x cube, meets the curve again at P2. In the same way, if we make a tangent at P2, it meets the curve again at P3. The tangent at P3 meets the curve again at P4, and so on. We need to show that the abscissas or the x coordinates of these points P1, P2, P3, etc., they are in GP, and hence we need to find the ratio of the area of triangle P1, P2, P3 and the area of triangle P2, P3, P4. So let us start with the problem by considering the point P1 to be equal to x1, y1. This is the curve y equals x cube. Let us say this is the point P, x1, y1. Any tangent made on this curve at the point x1, y1, this is the tangent meets the curve again at P2. Let us call it x2, y2. So we have y equals x cube, and since x1, y1 is satisfying the equation of the curve, we have y1 is equal to x1 cube. This is our second equation. Our slope of the tangent is dy by dx, which is equal to 3x1 square at the point x1, y1. So let us write the equation of tangent. Y minus y1 is equal to 3x1 square into x minus x1, on simplifying which becomes y equals 3x1 square x minus, since y1 is x1 cube, we have minus 3x1 cube plus x1 cube to be equal to minus 2x1 cube. This is our equation of tangent. As we proceed with the problem, we will see that although the problem appeared to be lengthy, if we go on step by step, we will see that it is actually very easy problem just by applying simple concepts of differential calculus. Now in order to get the coordinates of point P2, what we need is the point of intersection. It is the point of intersection of the tangent at the curve. So solving this equation with the curve y equals x cube, we have, putting y equals x cube in this equation, we get x cube is equal to 3x1 square x minus 2x1 cube. Now very obviously, one of the roots of this equation, which is a cubic equation, can be seen clearly to be equal to x1. So let us consider the other two roots to be x2 and x3. This cubic is equal to x cube minus 3x1 square x plus 2x1 cube. On opening the brackets and comparing the coefficients of x cube, x and the constant term, we get x2 to be equal to x1 and x3 to be equal to, or rather we can write it as x2 dash, because x3 will be the coordinates or the x coordinate of the point P3. So we should not confuse that with this x2. So we write this as x2 dash instead of x3. So the value of x2 comes out to be equal to x1 and x2 dash comes out to be equal to minus 2x1. Definitely x2 cannot be equal to x1 as the point of coordinate of the point P2, because it is already the x coordinate of the point P1. Hence we reject this x2 equals x1 and take the x coordinate of the point P2 to be equal to minus 2x1. Hence our point P2 comes out to be equal to minus 2x1, comma, since y2 is equal to x2 cube, since x2 comma y2 is lying on the curve y equals x cube, so y2 is equal to x2 cube. So this will come out as minus 8x1 cube. Now we are given that if a tangent is again made at the point P2, it will cut the curve again at the point P3. So doing all the steps again, we'll see that point P3 will come out to be equal to 4x1 comma 64x1 cube. We just need to do the steps which we did for the points P1 and P2 again for the points P2 and P3 to get the coordinates of P3 as 4x1 comma 64x1 cube, and hence we can see that x coordinates or the abscissas for point P1, P2, P3 are x1 minus 2x1, 4x1. Very obviously the common ratio over here is minus 2, over here is minus 2. So the abscissas of point P1, P2, P3, and in the same way for P4, P5, P6, etc. are in GP. Hence we have proved the first part, in which we needed to prove that if the curve are having the points P1, P2, P3 on them, then the x coordinates of P1, P2 and P3 will be in GP. Our P1 was x1 comma y1, or rather x1 comma x1 cube. P2 was minus 2x1 comma minus 8x1 cube. Our P3 was 4x1 comma 64x1 cube. Now we need to find the area of triangle P1, P2, P3 upon area of triangle P2, P3, P4. For that we require the coordinates of point P4, and since we know that x1, x2, x3 are in GP, so x4 will be equal to the coordinates of point x3 into the common ratio, which is minus 2. So this becomes minus 8x1 comma minus 512 x1 cube. Since y4 is equal to x4 cube, since x4 comma y4 are again lying on the curve y equals x cube, hence this area will be equal to half of determinant x1 cube 1 minus 2x1 minus 8x1 cube 1 and 4x1 64x1 cube 1 whole modulus divided by modulus of half of determinant area of triangle P2, P3, P4 minus 2x1 minus 8x1 cube 1 4x1 64x1 cube 1 and minus 8x1 minus 512 x1 cube and 1. This area we have written by using the formula for the area of a triangle if the three coordinates are given to be equal to x1 y1, x2 y2 and x3 y3. Then the area of this triangle is equal to half of determinant x1 y1 1, x2 y2 1 and x3 y3 1 whole modulus. We have used this formula to write the two areas. This is an important formula and you should remember this formula always. Hence, now we don't need to expand the whole determinant. What we can do is, we can take a x1 common from the first column, x1 cube common from the second column. So, x1 power 4 will come as common from out of the determinant, and similarly x1 power 4 will also come out as common from this determinant. This half and half will get cancelled and we will get 1, 1, 1, minus 2, minus 8, 1, 4, 64, 1 divided by, this is whole modulus, divided by modulus of determinant minus 2, minus 8, 1, 4, 64, 1 and minus 8, minus 512, 1. What we have done is we have taken x1 common from the first column and x1 cube common from the second column in both the determinants of the numerator and denominator. Now we don't need to expand the whole determinant. What we can do is, as we learned in the chapters of determinants, We just try to create two zeros which will ease out the problem. We can see that a zero can be created by subtracting R2 minus R1 and R3 minus R1, and again two zeros can be created in the denominator determinant by using the operation R2 minus R1 and R3 minus R1. So on using the operation R2 minus R1 and R3 minus R1 in both the numerator and denominator, we have modulus of determinant. The row first will remain as it is because there is no operation involved on row R1. This becomes minus 3, minus 2, minus 1. This becomes minus 9. This becomes 0. This becomes 4 minus 1, 3. This becomes 63. This becomes 0. This becomes, or this is minus 2, minus 8, 1 as it is. This becomes 6. This becomes 72. This becomes 0. And this becomes minus 6, minus 504 and 0. Now we could either solve the problem by taking a 3 common from this row, a 3 common from this row, a 6 common from this and a 6 common from this, and expand the both of the determinants to get the final answer as 1 upon 16. And hence our final answer is that the x coordinates of the points P1, P2, P3 are in GP. We have proved this, and hence the area of the triangle P1, P2, P3 upon area of triangle P2, P3, P4 has come out to be equal to 1 by 16, which is our final answer.